Hi there, Turgeon here, bringing you physics from afar. Is this the last one of the year? That's quite possible. Let's go. Session 2, I believe we left off on number 39. Let's make this stick, make this click. I'm going to go fast, but your job is to learn this stuff, make sense of this. This question, number 39, is really all about mechanical versus electromagnetic. So that's all about medium. Sound needs a medium. Electromagnetic waves don't. The answer is A. Number 40, velocity. Velocity, slope, acceleration. That's what you're supposed to think. If you didn't know that, it's okay. Now you're remembering. So this, when I look at this, I see a constant slope. Therefore, the acceleration is not changing. It does have an acceleration. The velocity is increasing, but it's increasing constantly. So the answer is C. In this case, I see an object with friction. It might be moving, but it's got friction in the opposite direction. So it eventually comes to a stop because of friction. Answer is B. Number 12, electrical force. As soon as I see electrical force, it makes me think of this equation. Your equation sheet is a valuable resource, is it not? So now I look at that distance and I think, oh, as the distance increases, the force decreases. That's what this graph is showing. Something's increasing and the force is decreasing. The answer's got to be D, 43. When I look at this, all these different wave properties, I think about, for this one, I think, electromagnetic waves, they're definitely transverse. Electromagnetic waves can go through a vacuum. In fact, they go at the speed of light. They slow down, though. They slow down when they go into a solid from a gas. So it's got to be choice B. Only properties 1 and 2 are correct. We're going to do some calculations. I know, we're going to do some calculations, but first we're just answering this question. The heat flowed from the water to the air. How do I know that? Because it had a higher temperature. The water had a higher temperature than the air. The other reason I know it flowed is because the temperature decreased. They wanted specifically for me to refer to the data. So because the temperature decreased, I know that it lost energy and I know the water must have flowed out. After a while, the room is still 23 degrees Celsius because it's huge. It's very hard to change the temperature of something so massive. So no, they did not reach thermal equilibrium. Maybe after like another hour or so, the water temperature is going to go down to the room temperature, and then they would have reached thermal equilibrium. Part D says calculate the change in thermal energy. Listen, MCAS tip. If it says calculate something and you really don't know, and we've never said calculate the change in thermal energy, that's got to be heat flow. Why? Look at your equation sheet. That's the only thing that makes sense. You've got a mass of the water. They gave you the specific heat of the water, and Q is the thing we want to calculate. Now, the temperature change here, you got to look at the table for that. So I'm just showing the temperature change. And I know they gave you a different kind of unit for a specific heat. Sorry about that. They did it in joules per gram. That's not something they usually do. Ohm's law. So for part A, first I look at these two circuits. They say this has the same total resistance. Therefore, I can just get the total of these because they're in series. So the total is the total of all those. Then it says calculate the current. Ohm's law, V equals IR, voltage, current, resistance. 0.5 A, the capital A means amperes. That's the unit of current. Now, this is going to increase the current because this one's unaffected, and when I add this, I add more current to the circuit. It's not the same as adding one up here. That would slow the current down. This is going to increase the current because this is unaffected. You still have 0.5 amps here, but we're going to have more current flowing here, so the battery has to supply more current. That's my answer to C. Now, they tell you to add a resistor. If I add it here, it will not affect what's happening over here because it's on its own loop. You might think add it here or add it here. No, that's going to slow the current down everywhere. It's going to slow because that current eventually comes through here. That current eventually comes through here. So can't add it here because that slows it down everywhere. It creates almost like a backlog. That resistance affects the current everywhere in the circuit. So it's the only place I can really add it. This has been Physics from Afar. I would say good luck, but you don't need luck. You need skill, knowledge, practice. Take care.